Good afternoon, everybody. Welcome to this week's edition of the Quantum Computing webinar series, which is jointly organized by Duke University, NC State University, and USC, the Rethink Labs at UNC Chapel Hill, Rethink Labs from the Kenan Institute. It is my pleasure to have covering a topic that hasn't been covered in this series before. The title of the talk is Improving the Efficiency of Payment Systems Using Quantum Computing. And it will be presented by two people today, actually, both from the Bank of Canada. Ajit Desai is a senior data scientist at the Bank of Canada. And we will have our first female presenter in this series. Danica Marsden will be also joining the presentation today. Since we're talking about payment systems, I'd like to actually briefly take this opportunity for those who are interested. Of course, payment systems have, technological innovations in payment systems have received a lot of attention, and the one that is the most in the public eye is probably everything that is based on blockchain and related to cryptocurrencies, stable coins, and the like. And I'd like to actually draw your attention to the fact that the Kenan Institute, the Rethink Labs of the Kenan Institute, will host, in partnership with the Milken Institute and the Fuqua Business School at Duke, a two-day conference, March 2nd and 3rd in Washington, D.C. in the Gallup building. Day one is focused on regulatory issues, policymaking, and practitioners, whereas day two is actually a repeat of a conference that my colleague Cam Harvey and I organized in Chapel Hill last year. It was the first academic DeFi conference, decentralized finance conference. So this year we will have our second decentralized finance conference co-organized by Cam Harvey and myself, and it will be preceded by a day of industry and policy discussions on that very important topic. But equally important, and perhaps less obviously in the public eye, I think, is issues about quantum computing applications. And I'm really delighted that
hey too.
Desai.
Give me 1 second. I need to.
That we have the Bank of Canada, whose presentation will be today featured, that Ajit Desai and Danica Marsden will be presenting their work. Ajit, I think they will be sharing the presentation, and if I'm correct, Ajit will start. Thank you. Welcome.
Thank you, Eric. Yeah, hello everyone, and thank you for joining us. Myself, Ajit Desai, I'm a principal researcher at the bank, and I would like to start by thanking organizers of this Quantum FinTechs webinar series, specifically Eric, for inviting us to share our project. And we are looking forward to that today. So along with Danica, my colleague at the bank, will present our project, Improving Efficiency of the Payment System Using Quantum Computing. And this is joint work with the researcher from the Good Lab Studio, Christopher McMahon, Donald McGilvray, JP Lam, and Thomas Liu. And from the Bank of Canada, we have Francisco Rivadeniera, Danica Marsden, and Vladimir Skavish. So, but before we jump onto the seminar, I would like to point out that these are our own views and not necessarily represent those of the Bank of Canada or other affiliation. So with that, let's get started. So this is an overview of our presentation. In the next few slides, without going into too much technical detail, I will first introduce the high-value payment system and the complex combinatorial optimization problem arises in them, for which we think the quantum computing is well suited to tackle. And then we will have see how quantum computing-based optimizer can be used as a preprocessor to solve the problem in order to improve the efficiency of the high-value payment system. And after that, Danica will take over to give us an overview of the quantum optimizer and settlement optimization algorithm we have devised to solve that problem. And finally, I will come back and present some of the results when we apply this algorithm on the actual settlement data from the Canadian high-value payment system, and then we'll conclude our findings. So the high-value payment systems such as Lynx in Canada, Fedwire in US, and Target2 in Europe are the central piece of the this country's financial infrastructure. And this system processes payments between the large financial institution on average equivalent of value of an annual GDP each week. So that tells us about the gravity or the size of this payment system. And these payment systems are liquidity intensive because the payment requests in these systems are indivisible and they need to be settled in real time on gross basis. Therefore, the bank participating in this system need to allocate billions of dollars of collateral for the purpose of funding those liquidity. To give you an example, Canadian high-value payment system have 17 participants, and on average each day in 2019, these participants exchange about 40,000 transactions, which is worth about $190 billion. To settle these payments, each participant need to pledge collateral. That is, at the system level, they pledge about $15 to $20 billion in Canadian high-value payment system each day. Generally, Canadian high-value payment system is comparatively smaller than US and Europe systems. So these numbers are much bigger for US, UK, or Europe's high-value payment system. And they can show us the sense of importance of system and also help us to understand the benefits of improving the liquidity efficiency. So in the next few slides, let's see how we can do that using quantum computing. So in order to do that, first we have to understand the trade-off which arises in this system. So the efficiency of this system is determined by the amount of liquidity that financial institutions choose to allocate as a collateral to the system and the timing they choose to process their payments request. And that leads to this interesting trade-off between liquidity and delay. So bank needs to navigate this trade-off in order to efficiently use the available liquidity. And they can do that by pledging more collateral, which of course increases the opportunity cost, and use it to settle the payment faster, which decreases the delay cost. Or what they can do is they wait for incoming payment to recycle the liquidity, but that has a high delay cost because they have to delay some of their payments, but the opportunity cost will be smaller. So here, if you think of the opportunity cost, what we mean by that is instead of using more collateral or pledging more collateral to the system, which needs to be collateralized, using their assets, which they can use it somewhere else. So there is a lost opportunity. So that's we are meaning to the opportunity cost. And also the delay of the payments could also have a costly because some of these payments could be very time sensitive and their clients could get upset and take their business somewhere else. So that accounts for the delay cost. In general, if you look into this, this is a not new problem in the literature, and they have tried to tackle it in a different way. So if you see, there are basically two ways to mitigate this liquidity delay trade-off. First is to change the incentive of the participant for the timing of payment submission so that the payments are more coordinated before they are coming to the system. And the second is to change the order in which the payments will be settled into the system after they come inside the system. And inherently, the second approach has a reordering, requires reordering, and that means there will be a delay incorporated with that. And in this paper, we take the second approach. So let's see the challenges we have to face or overcome in order to do that. So we want to find the best order or the right order in which a transaction should be settled so that reduces the total liquidity needs without significantly adding the delay. But going this way leads to a type of complex combinatorial optimization problem, which is a kind of NP hard and which is very difficult to solve. And because the problem goes to an enormous size with just a few outstanding payments, for example, if you take 100 payments, there are 10 raised to 158 possible combination in which you can settle those payments. And that's where we think the quantum computing have a competitive edge over the classical computers. But before we dive into this quantum computing, let's spend some more time to understand a little bit more about the high-value payment system and what do we mean by specifically the liquidity efficiency. So by liquidity efficiency, we mean the ratio of aggregated payment values over aggregated liquidity used at the system. So in other words, it indicates the number of dollars settled in the system for a given dollar of liquidity. So if you can increase the total value settled in the system for each dollar of liquidity, that means the system is more efficient than the previous one. So let me walk you through this slide in order to understand this better. So imagine we have P participants in the system indexed by an alpha. So N alpha T is participant alpha's net liquidity position until some time T in a day. which includes the initial liquidity, incoming payments, and outgoing payments. So as the payments are made to the system, their net position is going to change. So let's imagine that you start with a zero initial liquidity, and if you are sending a lot of payments and receiving fewer payments, that means your debit position is going to be higher. In other case, if you are receiving a lot of payments and sending less payment, that means your credit position is going to be higher. So in this case, when you start with a zero initial liquidity, what we care about is a debit position, because the maximum net debit position at any given point in time would tell us that what would have been the liquidity needed into the system in order to process those transactions in that particular order. So if we know that, then reducing the maximum net debit position across all the participants in the system implies an improvement in the liquidity efficiency, of course, holding that total payment value constant. So currently, we believe the financial institution participating in this high-value payment system typically choose the liquidity levels and prioritize their payments based on the individual business practices, industry guidelines, and payments level of urgency. But in this case, we are exploring a better way for improving the efficiency of the high-value payment system by reducing the liquidity need without adding too much delay. And we want to do that using Quantum Optimizer, which we are going to overview in the next slide. So on a typical day, high-value payment system was this way. So at the beginning of the day, each participating bank apportions some collateral to the central bank, which then grants some liquidity, which is we call initial liquidity, in proportion to their apportioned collateral. So these banks can now use that liquidity to settle their clients' payment as they come throughout the day. So as mentioned earlier, these payments requests need to be settled on the gross basis and only if they satisfy certain risk control of the high-value payment system. Specifically, that they have to have enough initial liquidity in order to process those payments in that order. So typically, this system has some liquidity savings mechanism, which can help us reduce the liquidity need by finding a potential offsetting position. However, such liquidity saving mechanisms are based on heuristic and do not search for the entire solution phase to find the best optimal solution. Therefore, these often leads to a suboptimal solution and with an increased delay cost. So what we are doing here is we are proposing quantum computing-based queue optimization algorithm as a preprocessor to the system, as shown in this as a centerpiece of this plot. So in our approach, before submitting the payment request to the system, each bank submits its request to the centralized queue, denoted by those P1, P2, P3, and Pn. So that's the original submitted queue. And once there is enough payments in the queue, let's call it a batch, the quantum optimizer processes that batch of payments and provides a new queue, which we can denote as a Q1, Q2, Q3, and Qn, in order that minimizes the liquidity requirement. This revised queue is then sent to the participants, and if they accept it, those payments are submitted to the system in the new order, which is suggested by the quantum optimizer. And we will demonstrate that our quantum optimizer can reduce the liquidity requirement using in this high-value payment system without adding too much of delay. And I'm sure now you want to know more about this quantum optimizer. So in coming slide, Danica will walk us through that. So over to you, Danica.
Okay, so why quantum? Why not use a regular classical computer for the preprocessor? As Ajit said earlier, reordering these payments falls into a class of problem known as discrete combinatorial optimization, growing specifically as order n factorial, where n is the number of payments which need to be reordered. Generally, for real-world problems, this actually scales faster than exponentially. In addition, constraints can add to the problem complexity. Normally, a classical or regular computer would seek the optimal arrangement by searching the solution space landscape, using methods such as gradient descent to find a path to the global minima, following the direction that leads downhill fastest. Next slide. However, in our type of problem, the landscape is really just islands. A classical solver now has to hop between the islands in this disconnected domain, using trial and error to exhaustively search them all for the best solution. Typically, using a variant of branch and bound might be what gets used in the software, especially if there is no structure in your problem, which heuristics can take advantage of. Another way to view this is that your constrained problem now has an additional set of constraints on the variables, which now also need to be satisfied, a very strong non-convex penalty term that only vanishes at the integers. So even if the rest of the objective is simple linear, the overall problem has lots of narrow local minima. Meanwhile, there's empirical evidence that quantum computing and quantum annealing, a specific type of quantum computing, are well suited to this type of problem. We know that qubits, the basic Lego building blocks of quantum computers, can work together to search a solution space like this all at once in theory, due to their intrinsic properties of superposition, entanglement, interference, and tunneling. Next slide, please. Due to the size of the problem we're trying to tackle here, how that translates into variables and constraints mapped to the qubits and couplers that connect them, of all the quantum computer prototypes currently available in the cloud, only D-Wave's quantum annealer, a heuristic and probabilistic solver, was large enough to handle the scale of our problem. The quantum annealing process moves the state of the system of qubits from a generic state to the landscape that represents the problem you're trying to solve. The 5,000 plus qubit annealer chip sits at the center of the middle circle here. It is about the size of your thumbnail, and around the edges, you see the wiring bringing the signals in and out to the chip. This sits inside the cryogenic fridge pictured at left, so it would be in the silver can at the bottom. And all of the rest of the infrastructure is just to cool this processor down to about 0 degrees. And then all of this would be contained within shields to protect the chip from magnetic fields and such. D-Wave's software platform, which combines classical and quantum resources, contains several solvers, but we ultimately used the constrained quadratic model hybrid solver. Go back. Which can take 500,000 binary and integer variables and 100,000 linear and quadratic constraints, inequality as well as equality. Even with this solver, we can only consider reordering as many as 700 payments at a time, and we'll show our exploration of performance as a function of batch size later on. Next slide, please. In order to program the problem and run it on the D-Wave hybrid quantum solver, we must cast it into one of a few formats. Here, we've posed our problem as an objective or cost function, the top line equation, as well as 3 constraints. The objective function simply seeks to minimize the extra liquidity required to settle the batch of payments, denoted here as B, over all financial institutions alpha. The final 2 constraints are symmetric and ensure that each payment is settled once and only once, where x, I, t are decision variables equal to 1 if payment I is settled at time t or 0 otherwise. The economic intuition of the problem is summarized by the first constraint. N alpha of 0 is a participant's net position at the start of a batch, their starting balance. This plus the value that is settled in the batch to that point, f, the value of the payment, times x, gives the participant alpha's net position at time tau. F times x can be positive or negative depending on if the institution is a payer or payee. The total liquidity available to settle a given payment is then these 2 terms, N alpha of 0 plus f times x, the net position at time tau, plus their maximum net debit position, MNDP, incurred from previous batches. At time tau, MNDP alpha is already predetermined or fixed, as is N alpha of 0. Thus, we see that if N alpha of 0 and MNDP alpha can't cover the cost of the batch of payments, f times x, then we need B of alpha, extra liquidity required to settle the batch, which is what we want to minimize. A marginal increase in f times x means more payment value is settled, but also requires more liquidity B. However, increasing B deteriorates the solution, requiring additional liquidity in the system above the MNDP observed up to the processing of that batch. Next slide, please. The hybrid solver will run many times and ideally return many feasible solutions of the form illustrated here as a matrix. The rows represent the original payments order I, and columns represent the new ordering T. So for this fictional batch of 7 payments, the payment that came into the original FIFO queue fourth would now be processed first. The payment that came into the queue first is now processed second, and so on. All transactions are settled once and only once. You can see this because there's only 1 1 in each column and row. So it meets those constraints and all payments in the batch were settled. And this solution matrix should have found a reordering that minimized the required additional liquidity needed to do so. Now, this is a heuristic, so we have no guarantee of optimality, but if we see many feasible solutions returned, we choose the solution with the highest frequency and lowest energy, which will likely be the best solution found by the solver. For a batch of 70 payments, we get about 40 solutions with many repeats. Next slide, please. Putting this all together, the quantum algorithm is comprised of accumulating the batch of payments to reorder, constructing the decision variables, cost function, and constraints, which feed into the CQM object and CQM solver. We send that to the D-Wave machine in the cloud. It runs a bunch of times, you get your answers back. And then you process the return results to come up with your new ordering. We want all of this to take no longer than the time it takes to accumulate the next batch of payments in order to prevent a backlog from accruing. For a given batch size, this algorithm is run on 30 days of data.
Thank you, Danica, for excellent overview. So now we understand the problem and our algorithm and the whole setup. So let's see how we can the performance of our algorithm on the 30 days of the sample from Canadian High Value Payment System. So from those 30 days, we only chose non-urgent payment requests because they have a low delay cost, and urgent payment requests could have high delay cost. So we and inherently applying this algorithm to collect the certain batch of payments, we have to delay the payment. So we focus on that non-urgent payments. And the frequency at which the payment requests are submitted varies with the time of the day, as you can see on the plot on the left. So we see a much higher volume of payments settled between 8 and 9 a.m. and the number of payment requests remains steady from about 9 until 4 p.m. before they taper down towards the end of the day. So this suggests that wait time to collect the certain batch size of the payments varies throughout the day, and it could be much higher towards the end of the day. And also, if you see the payments amount settled for each of the transaction in our sample, more or less they follow the uniform distribution across the day as shown on the plot on the right-hand side, where the y-axis is the payments amount and the x-axis is the submission time. And however, if you observe closely, the shares of the payments with the high payments amount is higher towards the middle and later part of the day. And also these, there are some large value payments like a 2 billion or slightly higher than that, and they could be challenging to reorder, and that could have a strong influence on how much liquidity we can save when those payments are part of that particular batch. And we will show some of those results in our next few slides. So given our algorithm works on the batch of the payments using that sample from Canadian High Value Payment System, first we want to choose the batch size, which can work best for us. And to do that, first we look into the wait time. So that is the time it takes to collect the fixed batch of payments to be optimized by the quantum optimizer. As you can see in the plot on the left, wait time increases linearly with the queue size. And the variation captured by the standard deviation grows with the batch size as well. And this is primarily due to the variation in the intraday frequency of the payments arrival. The plot in the middle shows the time it takes to compile and solve the optimization problem. So along the increased batch size. And here, both compile time and solve time increases cubically with the batch size, more or less cubically with the batch size, suggesting the limitation on the maximum size of the problem we can solve without adding too much delay in our collecting those payments. Similarly, the plot on the right, we show the number of feasible solution. I think Danica alluded a little bit on that, which is in quantum computing is positively correlated to the solution quality. So this plot suggests that the solution quality decreases with the batch size, and this deterioration rate is much higher when we go, in our case, beyond 150 payment size, for instance. So in this case, the hybrid CQM solver, we have used a certain fixed parameter, including amount of time specified in the solver. And if you use the default maximum time allocated by the D-Wave CQM solver, with a higher batch size, we get a fewer and fewer solution. And in this particular case, with a 700 batch of payment, we did not get too many feasible solution. However, what we did to test our algorithm, we let for that particular case, which is highlighted here with the red star on the rightmost plot, we let it run for the higher time, and we saw that the number of feasible solution increases as we let it run for the longer time. So it is possible to get a better solution with a higher batch, but the delay cost would be much higher than what we can afford to wait for in this case. So using this plot, we can choose to use this particular batch. Like across these three plots, we saw that 70 batch would be good for testing the performance of our algorithm. So for the batch of 70 payment, aggregated wait time is about 90 seconds, and compile and solve time is about 10 seconds. So that while we wait to collect the payments, we can easily solve the problem, compile it, and pre-process it and post-process it, and all those can be done within that time. And also the solution quality is higher. So let's see how that using that batch size or the performance of this algorithm for the entire sample. So these are some of the key results. So in this particular case, we run the day-by-day horse race between the original order, that is the order in which the payments came and then settled. So we call FIFO or first in, first out. And we compare that with the CQM proposed order. That's where our quantum optimizer is proposing. And we start both for this particular horse race, we start the day for both of them with the same initial liquidity. So we saw on average across 30 days in our sample, our algorithm could able to save about $240 million end of day liquidity savings with a medium about 130 million and a maximum is 1.3 billion. So this is compared to the original order, that is when those payments are settled in the FIFO order. So to get an intuitive sense of these savings, let's say by doing backup envelope calculation, because it's very hard to put the cost to the opportunity or delay cost to quantify those value. So it was about $4,000 to use this use the quantum computer for the day to run in our case, and the marginal saving in terms of opportunity cost is about $250,000. So even with the current quantum hardware, which is still evolving and expensive to use, the marginal gains are good. That's one of our conclusion from this. Now, if you look into each of those batches, the number of batches which are optimized during the day across all days are about 26%. So this might feel small, but if you take a closer look into these batches with the 70 payments, only about half of them are optimizable. That is, at least few participants move their maximum net debit position in the FIFO setting. So our quantum algorithm has an opportunity to find the order, better order. So those batches we cannot do much. From the remaining about 50% which are optimizable, in many cases, there are participants who had only outgoing payments. So you cannot do much again with that because no matter where you send that payment, that participant is going to have a similar max net debit position. And sometimes FIFO is already being optimal in our case. And sometimes there is a very large payment which you cannot offset. So these things further reduce the opportunity cost, and that brings down the total fraction of batches we can optimize to the 26%. In retrospect, we think that we should have considered this as another aspect while selecting the batch size, and we plan to do that for the future. So we also run a batch by batch horse race. So for each of this batch for FIFO and CQM order, we restart your initial condition and rerun the batch by batch for horse race. So we find on a typical day, an optimized batch saves about 13.2 million on average, with a medium of 0.8 million and maximum of 340 million. And occasionally, the order returned by the CQM hybrid solver returns a less efficient solution compared to the FIFO. But this occur in our case only a handful of times, and the loss in savings were comparatively much smaller. So on the slide, as an example, we have shown the net position of each of this bank involved in a typical batch. And this plot shows the participants' changes in credit and debit position after each transaction settled in that batch, where each of this color is coded by those for each of these participants. So for the top is your FIFO order and bottom is the CQM. So we can see that the CQM could able to reduce the maximum net debit position by about 10 million in this case. And how it does that by actually delaying large value payment. So if you can see this, focus on these red stars. So that particular purple bank had a very large payment at the earlier part of the batch. What quantum or CQM does is try to push that payment towards the end of the day and try to settle all other small value payments earlier part of the batch. And this is one of the way we saw that what is the quantum optimizer doing in our case, and that gave us an intuitive understanding of how this algorithm is working, and also help us to build a confidence on this algorithm. In the next slide, we also examine how equally these savings were distributed across the batch, because most of the time we are looking at the system level liquidity savings, and that is good, but we also want to see that how that savings are distributed across each of these participants, which are contributing towards that final savings. So in the plot, we compare each participant liquidity saving to their net total incoming and outgoing fraction of the payments. They are the total value of the payment they are settling into the system. And we find that the percentage of the total amount saved for each of these participants is positively correlated to their percentage of total incoming and outgoing transactions. In other words, if you want to get into understanding, if a participant is involved in a payments responsible for half of the total settle in that particular day, then it is highly likely that they are going to see half of the savings from the whole system. So next, as an example, we show the evolution of the aggregated max net debit position for a typical day in our sample. So with a batch of 70 payments at the start of the day, as participants send many payments, we see a sharp rise in aggregated max net debit position. But as the day progresses, however, we see a slower increase in the max net debit position. So for many batches during the day, no participant had moved their max net debit position, and thus no rearrangement could provide liquidity savings. And some of those cases are non-optimizable batches. And these that can be seen as those flat sections of the curve on the plot, where the blue line is the FIFO, orange line is the CQM with a 70 batch size. And we can see that the performance on the same day is better if we increase the batch size from 70 to 140, as shown by the green curve compared to, and if you compare that with the orange curve, which is for the batch of 70. So clearly, the chosen batch size, there is a significant heterogeneity across the batches, and there are limitations on the improvement which can be achieved with this simple pre-processing setup, where we have a fixed amount of batch, and that is it's a much smaller size. We think that if there is a scope to improve this by making it flexible or trying to find the best size of the batch, which can be given to the quantum optimizer rather than giving this fixed batch of 70 payments. And that can be further emphasized by using this table. Here we can see that we went for a couple of days in our sample. Instead of 70, we also look for the 140 and compare it back to the 70 batch size. So we observe the number of batches that see higher savings, or the FIFO increased by about 15% for both the days in our sample. And this is certainly due to the increase in both amount of liquidity available to recycle and the increased connectivity between the payers and payees. So as you have more payments in a batch, there is a highly unlikely that there will be only one participant only outgoing payment. So, and they might have some incoming payments. So there is a more possibility that for the CQM optimizer to reorganize them in a better way so that the savings can be observed. Also, one of the most encouraging improvement we saw is the end of day liquidity savings, where these 2 days sees an increase in approximately about 10 times and 2 times end of day liquidity saving for those 2 days selected in our sample. So that brings us to the end of our presentation. So some of the key summaries are that we developed this new algorithm to optimize real-time gross settlement of payments, and we test it on a high-value payment system by incorporating it as a centralized preprocessor into existing high-value payment system without requiring a fundamental change into their risk models. And we saw that despite there is a limitation on today's computer in terms of the size and the cost, our algorithm provides significant liquidity savings when tested on the data from coming from Canadian high-value payment system. And we think that we demonstrate the usefulness of this quantum computer for practical application, which could pave the way for future research as these algorithm and this technology going to mature.
Thank you so much. Oh, you're not finished.
Just one last thing.
Go ahead. Sure.
No, just a couple of things like what we want to do with the future. As we saw, as we went through the results, that finding an optimal and flexible batch size could have more potential and could give us more savings and have more impactful outcome. And of course, we want to do is like benchmark against the other liquidity saving mechanism, which are already part of some of this high-value payment system. And of course, we want to look at the state-of-the-art classical heuristic solver and compare them against the quantum and see how our algorithm performs against that. So if Danica or Francisco both are here, if they want to add something at this point, we have a couple of minutes in the allocated time.
Thank you. We have plenty of time for questions. Maybe to make it easy, I would suggest that you might write your questions in the chat. maybe I'll start myself with a few questions, if that's okay with you. So this reminds me of trade matching algorithms in, say, dark pools and the like. Have you sort of have you explored the similarities and differences between, if you're aware of the trade matching dark pool kind of algorithms? I remember that at the at the IBM Q Network conference, Barclays in 2019 was presenting a trade matching quantum algorithm that sort of looked very similar.
Unfortunately, we haven't explored in that direction, but maybe somebody, my co-authors might be aware of that.
Thank you, Eric. This is a very good question. In fact, we haven't specifically thought about using it in other financial market infrastructures. But what we've thought is, to the extent that that Hamiltonian, so basically the quadratic problem, is basically a general problem that tries to offset positions, right, in batches.
Correct.
So we do think that the Hamiltonian is probably a big contribution here. How to apply it to the machine, it's also very important, certainly. But to the extent that there's similarities between a high value payment system and any trading venue, I think there's applicability. I think a high value payment system is the easiest because we're trading the same thing over and over, just money, right? Just settlement balances. Trade venues are potentially a bit harder because the different positions are heterogeneous, right? It's like one type of security versus another. But if it were just one type of security, it would apply just equally to our setting.
Yeah, I mean, so in dark pools, or potentially centralized exchanges, but in dark pools, there might be the same security being traded, in the same kind of batch sort of ordering as you have in your payment system. And I think that's sort of worth sort of exploring, actually. So I think it has a lot of applicability beyond even this very simple setup. That's sort of what I wanted to alert to. And I can find for you the Barclays presentation. That's the one that comes to mind, because they were actually trying to do that in a dark pool setting. A little bit related to that is you keep talking a lot about savings, but who pays the cost of this system? Someone has to pay it, or is the Bank of Canada subsidizing it ultimately?
We could. It actually only amounted to about a few $100 a day.
So it doesn't matter that much.
Yeah.
I was guessing.
But I think, yeah, Eric, but there's another point beyond the actual computing cost, which is the incentives that participants would have to buy into this preprocessor, right? Because this preprocessor is basically like a central planner. It's taking all these payments with the order in which they're submitted, and it's reordering them. So what would be the incentives of a particular participant to have its payment delayed a little bit, right? We argue in the paper that given that these batches last simply 90 seconds, I don't think any participant would actually be able to try to strategically block a proposal of the reordering. But definitely there's an issue here of incentives.
And I'll ask the final question because I don't want to be monopolizing this conversation. So one of the things that you noted is that the large batches are delayed until the end. Are we talking about delayed within that 90-second window? Is that what we're talking about essentially? Okay, so that's not such a big deal, because if it were delayed further in the day, then this would be across batches. This would be more problematic for
And indeed, it's kind of well known, right? If you bypass, some of those liquidity savings mechanisms have bypasses, which basically force the large payments towards the end in the day. Effectively, what this algorithm is doing is trunking those payments and then settling in that period of time, but literally kind of pushing those big ones towards the end of that batch. You might argue, well, this is a game, right? So
Correct.
maybe participants will say, okay, I'm going to start putting my big payments earlier in the day, or start playing some kind of strategic game, right? So we didn't kind of think of that, but that's something that we've thought of thinking about.
Or splitting the large batches.
Yeah, if
in
it's possible,
order to
like,
have early execution.
yeah, most likely they can. Otherwise, they would do it today.
Right. Anyway, any of the participants want to chime in on this very interesting? So this is, maybe I'll just ask one final thing. So this is all experimental, right? You just sort of have done this on a historical data set. Are you thinking about implementing it in real time? Or is that not a good question that I should ask on a central banker?
So I'll probably can chime in, and Danny can also complement. So this is very early, right? As we're basically arguing, it's a preprocessor, and that would be kind of the politically feasible way of proposing this, because usually changing the risk model of a payment system is very, very complicated. It's very hard to get those participants to buy into a wholesale change to the risk model of a payment system. So I think we would need to do a lot of testing, a lot of work before this really gets into the realm of being implemented. So that's part of that future work that Danica is thinking of doing.
I guess one advantage is that you have a relatively concentrated banking sector, right? I mean, that makes probably the problem a little bit easier to get everybody around the table. We're diverting from quantum here, but I'm sorry.
It's okay. To add to that, though, I mean, when you talk about the infrastructure for quantum computing currently, you'd have to be sending protected data in the cloud to a quantum computer in the cloud, and that's not something we would do. So the infrastructure needs to be built up such that using something like homomorphic encryption or something along those lines, the data would remain protected in transit.
I hate to do this, but I have one more question, because so is the information transferred to quantum information, is that part of your processing time? Because I assume it's digital entering the system, and then you have to make it a quantum information representation.
So the time to translate the problem into sort of biases and make qubits and couplers to run the problem and get the solution is incorporated in that. It's about 5 seconds.
Okay. Because often that's not considered in the calculations of processing time. That's kind of...
So in fact, the transit time across North America from one side to the other is much, much longer. And that is something that, again, in the future with improved quantum computing infrastructure, you'd have quantum computers in the cloud placed everywhere. You're not just having to go from, say, New York to LA and back.
Right. If you have a question, please. I mean, the interesting about this webinar series is that we have a very multidisciplinary crowd. We have people in physics, we have people in math, we don't have many bankers. We don't have many finance people. I might be the only one on this call, hence my excitement, relatively speaking. But please feel free to ask a question if anybody wants to ask a question. Unmute yourself and introduce yourself.
Good morning. I have a question. I'd like to thank you for your presentation. I'm not a business guy, but can you tell us how many qubits do you need to describe the Hamiltonian? And is there a relationship between the number of qubits in the Hamiltonian and the size of the batches you're processing? Thank you.
Hi. Yes, so there is a scaling, and that sort of fed into why we use D-Wave in the first place. So the D-Wave quantum annealer currently has over 5,000 qubits. And forgive me if I'm not quite answering your question, but so feel free to chime in. But the annealer has over 5,000 qubits. Even so, that translates to about 170 fully connected logical variables. And so because of that, we in fact use a combined hybrid solver, which combines classical and quantum resources to be able to scale that up to more variables. So with the constrained quadratic model solver, which could take in 500,000 variables, then we could consider batch size up to 700. Although we found that there was sort of this sweet spot around 70 to 140 based on the delay time that was incurred.
Okay. Is that the latest D-Wave 5,000 qubits?
That's what's currently available. I believe this year they're planning on releasing something in the 7,000 range qubits. And again, that's an annealer. And then they have, I think, in their roadmap, some longer term plan to also release a gate model or universal quantum computer.
Thank you. In the future, do you have plans to move this to an IBM gate-based, maybe DQE eigensolver? You can, run optimizers, and it may be another research direction.
Yeah.
I don't know if that's in your plans in the future. Thank you.
I mean, certainly it's something you'd want to try, just as you would want to try different kinds of classical heuristic solvers. However, I mean, currently the largest gate model quantum computer that's available is the IBM quantum computer, which has about 430 qubits with only three-way connectivity, I believe. And I mean, they all have plans to release more, but they're all very small scale. And on top of that, they're not fault tolerant, which means, so they're not implementing something called error correction, which makes them robust to errors. So it's just the scale of those prototypes for the gate model quantum computers, you just can't run this kind of problem on. And we're probably several years out from that, but certainly when they come out, we would try.
Thank you.
I think just to add to that, like IBM, some of the researchers from IBM tried this kind of problem, not the high-value payment system, but different types of settlement optimization problem. And I believe with that, they went up to just like 7 payments in each batch or something like that. So that's the constraint they had. And with that kind of small constraint, probably in high-value payment system, we might not find any savings.
So for the short term, the D-Wave is the only platform that is capable of running your stuff. Is that correct?
That's correct.
Okay, thank you.
Well, to achieve meaningful results. Mm-hmm.
Thank you.
Yeah, for what it's worth, we had a seminar on the very first solution to a real business cycle model in October last year, and that was the same situation. The only way to implement it was on a D-Wave because of the constraints on the hardware in IBM and others. So you're in the same situation essentially.
And even I'll add to that. So we did actually look at using Skip, which is an open source classical mixed integer quadratic constraint problem solver. And it just uses classical resources. So, trying to solve these batches of 70 or 140, oftentimes it would take more than 2 hours for it to solve. And occasionally it would take, after something like 24 hours, it would fail. So, and that was running on an R5.4 X large AWS instance. So that just goes to show that these truly are difficult problems to solve.
Indeed.